Welcome back to our machine design series. Today we are covering an example of how to use combined loading conditions to find a predicted life of a particular bearing. So this is example 11-4 out of the textbook, and I have added a drawing here of what is described by this question so that you can really see what is meant by the term angular contact bearing. So when this question says we have an angular contact ball bearing, what that refers to is this shape of the inner and outer raceways that allows for this ball-shaped bearing to absorb both radial loads and axial thrust loads. So when we apply this axial thrust load to this ball bearing, the ball is going to contact the inner and outer raceway at these rounded corners that have been shaped by the inner and outer raceways. And that contact is what is allowing this bearing to actually take up axial thrust loads. So with that, let's add in here some more numbers. So this question tells us that our radial load is 2,224 newtons, that our axial load is 1,779 newtons. And we're also told that the outer ring is going to be stationary. So this is going to be fixed, and our inner ring is going to be the one rotating. And we are given a particular load rating for the bearing that we've selected. So our static load rating, C0, is given as 19,793 newtons, and our dynamic load rating, our C10 value, is given as 35,139 newtons. And remember that C10 value corresponds to a radial load at which 10% of a group of bearings have failed at our manufacturer's specified number of cycles. And let's say that this is an SKF bearing that we've spec'd, which means that the L10 life is 10 to the 6 revolutions or cycles. This is a constant factor for any one particular manufacturer, so SKF rates all of their bearings for 1 million cycles, and they provide their C10 load rating corresponding to that many cycles in all of their bearings. And lastly, this question asks us to find the L10 life of this bearing at 720 RPM. In other words, this question wants us to find the number of hours that this particular bearing can operate at 720 RPM. Okay, so using what we learned in our last video, we know that we are going to need this ratio of FA over C0 in order to use this table. So let me just copy this table and bring it down. We can use it in a second. Okay, so we need this ratio of FA over C0. Well, we're given both of those values, so we can go ahead and just plug those in. Our axial load was given as 1779 newtons, and our basic static load rating was given as 19,793. And when you plug that ratio into a calculator, you should get about 0.0899. So I come over to this table and I'm looking for a ratio of 0.0899. So that's somewhere between these two lines here. And so we're going to have to interpolate to find our specific value of E. So let's set up a little table here to do this interpolation. So the top line is 0.084 for my ratio of FA over C0, and that corresponds to an E value of 0.28. That's just this line from the table. And then the next line down is 0.110, and E is 0.30. I have a value of 0.0899, and so I need to do linear interpolation to solve for what the value of E should be. I am going to leave that to you and just tell you that the answer is 0.29. All right, so you can prove that to yourself. I have faith you guys can do linear interpolation. And with that, now we need to move to the right in our table and try to figure out if we are below or above this value of E. And remember what that means is we're trying to figure out where we are in this plot. Do we have a thrust load that is high enough that it has an effect on our bearing life? Or is our axial thrust load low enough that it has no effect and we're in this flat line region? Okay, so we're going to need to find the ratio of FA over VFR. Now FA, again, it's 1779, that doesn't change. V. Remember we said that V is our rotation factor, and that depends on whether we have the inner or the outer ring rotating. In this case, we were told that the outer ring is stationary, meaning that the inner ring rotates. That's what I drew these cross lines for, to denote that this is stationary. So when the outer ring is stationary and the inner ring rotates, V is equal to 1. If we had the opposite scenario, it would be 1.2. And the last thing we need is our FR, which was given as 2,224 newtons. Okay, so we calculate this and come up with 0.80. Now I need to compare this ratio to the E value that I solved for earlier, and it looks like this is greater than my E value of 0.29, right? So that means that FA over VFR is greater than E, which puts us on this side of the table. So our axial thrust load is high enough that it does have an effect on the equivalent radial load this bearing is carrying. So now we're going to need to get our X and Y values so that we can calculate what that equivalent radial load actually is. And remember, the equation for that is going to be FE equals X. I'm going to do x2 because we already know that we are on that side of the graph, plus y2 times FA. Okay, so we need to find x2 and y2. If I look at my table here, I can see that x2, no matter what I do, it's going to be 0.56. But now y2, it varies depending on this value of FA over C0. So I got to do linear interpolation once again. I'm just going to extend this table and add y2 in here. So we've got, for the top line, y2 is 1.55. For this bottom line, it's 1.45, and we need to do linear interpolation in between. Again, I'm just going to give you the answer, and you should check this for yourself, or maybe pause the video here, see if you can get it, and then I'm just going to tell you it's 1.53. So we've got values for x2 and y2, and we have our axial and radial loads, of course, so we are ready to calculate this equivalent radial load. x2 is 0.56, v is still equal to 1, Fr is 2,224 newtons, plus y2, we just found that it was 1.53. Oops. And we have our axial load of 1779 newtons. All right, so calculate that, and I got 3,967 for my equivalent radial load, and that is, again, in newtons. Now, we can use the equation that we developed in our lecture on bearing life, which was Fr times Lr to the 1 over a power equals F desired times life desired to the 1 over a power. And we have everything that we need to plug in here and solve for our desired life. So let's do that. Our rated load, this is our C10 value, which we were given in the beginning. That's this 35,139 newtons. Our rated life is 10 to the 6th revolutions. That's just something that's standard for all SKF bearings. A is going to be 3 for ball bearing. It's 10/3 if we had roller bearings. Our desired load is this equivalent load that we just came up with. This is an equivalent radial load. So that's 3,967 newtons. And we are going to solve for the desired life. But remember, the question asks us to get life in hours, so I'm going to go ahead and do this conversion inside this equation. We want our L10 life in hours, so I'm multiplying by 60 minutes per hour and by the speed of 720 RPM. And this is also to the 1/3 power. So we can solve for that L10 life just by doing a little bit of algebra. Okay, so when you do that, plug in those values. I just got 16,088 hours. Okay, so this is our predicted life. And remember, this has a 90% reliability built into it. So 10%, we predict 10% of a group of bearings would fail at this point of 16,088 hours in this particular scenario. So for this angular contact ball bearing with this exact loading, inner ring rotating, outer ring stationary, we predict a life of 16,088 hours. So I hope this video was useful. In the next one, we will talk about the American Bearing Manufacturing Association boundary dimensions so that you can spec bearings with particular width and diameter series codes. And then we will move on to journal bearings. So thanks for watching this video, and I hope to see you in the next one.